In this video, we're going to learn how to write the reaction quotient for generic reactions. Our work in the last couple of videos has been very useful in deriving an expression that is going to allow us to predict whether a reaction will be spontaneous or not under any set of conditions that we're interested in. That calculation only involves knowing the reaction gives energy at the standard state, which is something that we can obtain from standard tables, and then a correction, which just has the gas constant R, temperature, and then the reaction quotient, which is going to be kind of the body of this video. Right, so let's try to remember what a reaction quotient is for a generic reaction with two reagents A and B and two products C and C, which are multiplied by their stoichiometric coefficients, lowercase a, b, c, and d. The reaction quotient is simply the concentration of products in the numerator to the powers of the stoichiometric coefficients divided over the concentrations of reagents elevated to the powers of the stoichiometric coefficients. Right, so the way that you do that is simply say, well, that is the activity of C, the activity of D multiplied or elevated to the power of the stoichiometric coefficients, and then the activity of A, and then the activity of B also to the power of the stoichiometric coefficients. Now the real question is, well, these activities are not actual numbers. How do we actually put their molarities or partial pressures, things like that, right? So, well, we're going to write here a table that is going to allow you to do that mapping of activities into concentrations that we can easily handle. Okay, so that is going to be that table. All right, so let's see. This is going to be the meaning of the activity of J, okay, where J could be any component. And these are the various cases that we're going to handle here. Okay, so if this is an ideal gas, the way that you write the activity is simply the partial pressure of that component over the pressure of the standard state. Okay, so here we're going to write what the reference or standard state is. That pressure of the standard state is 1 bar, by definition. Okay, so just figure out, see how simple this is, right? So, activities have been place holding measures of concentration, but now we actually are going to be able to learn how to map those into something that is useful. Partial pressures, really easy to measure, very easy to understand, and this is simply 1 bar, right? So it looks like this is relatively straightforward. Okay, let's now look at solutes in ideal solutions, and this is going to be every time that you want to do a problem with solution, you're going to be looking at reagent or product species that are dissolved into a solvent, right? So they're going to be solutes, and generally they're going to be at low concentrations. So that means that you can generally apply the ideal solute equations. Excuse me. Let me repeat that. Again, when you think about chemistry in solution, the chemistry generally always takes place between solutes that are dissolved into a solvent at low concentrations. And when that happens, then you can apply an ideal dilute solution framework that allows you to do that mapping really straightforward too, right? So for a solute, and here there should be a condition in an ideal dilute solution, then this activity is going to be simply the molar concentration of that solute J over the molar concentration at the standard state, and that molar concentration of the standard state is by definition just 1 molar. Okay, so this looks pretty simple as well. Alright, these are going to be most of the cases that we're going to find in problems, but there's a couple more. If you have a pure liquid or solid, which they also appear sometimes, so pure liquids or solids, then the activity is simply going to be 1 by definition, which makes things really, really easy. Okay, so with this table that we have right here, there's other entries that we could use here, like ideal solutions, but they're going to be less important in the problems. then we can actually start to write here chemical potentials for any reaction that we really want. Okay, and then that will set up our calculation of this activity of the spontaneity of a chemical reaction. So in the remainder of this video, we're just going to take a look at a couple of examples to really show you how simple this is. Okay, so let's see maybe a reaction that we wrote a couple of videos ago, which was the reaction of nitrogen and oxygen in the environment to generate nitrogen monoxide, right? So O2 to generate 2 molecules of nitrogen monoxide. All right, so let's write the reaction quotient there. Okay, we take this placeholding expression and we're simply going to replace that. We only have one product, which is NO, so that will be the activity of NO to the power of the stoichiometric coefficient, okay, divided over the activities of reagents. Okay, so that will be N2 to the power of 1, and that will be the activity of O2 to the power of 1. Okay, so that is your reaction quotient, but of course now we want to replace this by concentrations or pressures that are easy to handle. So all of these are gases, and if we're working here under ideal gas conditions, right, the pressures are low, then we can simply just take each one of these activities and replace them by the ratio of the partial pressure of that gas over 1 bar. Okay, so this then is going to turn simply into the partial pressure of NO over the partial pressure at the standard state squared. And this is just going to be the partial pressure of NO of N2 over the partial pressure of the standard state. And that is simply the partial pressure of O2 over the partial pressure of the standard state. Okay? But of course, the partial pressure of the standard state are just 1 bar, so we can just go right ahead and write here 1 bar everywhere. 1 bar and 1 bar. And even though I think it's extremely important to always divide by the concentrations or pressures of the reference state, most people actually don't do this, which I think is short-sighted, right? So generally, the way that you see these expressions are something like this: P NO squared over P N2 partial pressure of O2. So that is your reaction quotient, right? So notice how simply we have mapped activities into concentrations that are easy to handle. Let's do one more example and then we'll wrap this up. Alright, so the next example is just going to be maybe a more complicated reaction that involves solutes, gases, maybe solids, and so forth. Actually, we can do here maybe the combustion of glucose as a solid. Right, so glucose is C6H12O6, which is going to be a solid in this case. We're going to burn it with oxygen to generate CO2, and then water as a liquid if we're doing this at ambient conditions. Alright, so let's write the reaction quotient for this. Well, there's just going to be the activities of products, activity of CO2 to the powers of the stoichiometric coefficients, activity of H2O as a liquid, 6, and then the activity of glucose, C6H12O6, which is a solid, and then the activity of oxygen, which is a gas, to the power of the stoichiometric coefficient. Okay, so these are our activities. We now come and replace those by our useful measures of concentration. Okay, the pressures are straightforward, right? So that is simply going to be pressure of CO2 over 1 bar to the power of 6. And for oxygen, that is going to be the partial pressure of O2 over 1 bar to the power of 6. Okay, great. And now we just have the solid and the liquid. But notice that these are now pure. Right, there's this solid is actually the activity is simply 1 for that one, and that liquid, there's no other liquid in the reaction environment, right? Water is the only liquid that you form. That means that the liquid is pure, and that means that the activity for that is simply 1. Okay, so that's a really simple reaction quotient that you find in this case. Alright, one more example just to illustrate here solutes. So now suppose that we're not doing this reaction with solid glucose, but we have glucose dissolved in water. Okay, so that is now it's not as solid, but it's in aqueous solution, right? So we can write that simply as parentheses AQ, meaning that it's a solid in solution. Okay, so here we'll have the activity of glucose, C6H12O6, in solution. And now we have to map it into an effective measure of concentration. So if this concentration is small, and we're working under ideal dilute solutions, and we're always going to be working on those conditions, then we can simply replace it by the molar concentration of that glucose over the molar concentration of the standard state. So that simply turns into C6H12O6, that molar concentration divided over 1 molar. Okay? Alright, so in the next video then we're going to see how to utilize this to predict the position of equilibrium.